Hello everyone. In this lesson, we will learn about matrix operations. And so by the end of the lesson, you will learn how to perform arithmetic operations on matrices in R. So if you recall the arithmetic operators that we have learned before, we do have the addition, subtraction, multiplication, division, exponent, modulo, and integer division. And their corresponding operators are shown on the screen. So for matrices, the main arithmetic operations would be addition, subtraction, and multiplication. There isn't any division, exponent, modulo, or integer division of matrices. However, if you want to extend the arithmetic operations to division, exponent, and the rest, it will only be possible when you are dealing with element by element operation, the likes of which can be done with addition and subtraction. So let's have a word of caution here. If you use the arithmetic operators, you are able to perform the element by element operations in matrices. So the two matrices must have the same dimension. But we are going to look at addition and subtraction of matrices first, and in which case, for any given two matrices A and B, addition and subtraction is possible only if A and B have the same dimension. So for example, if you have a matrix A and B of the same dimension 2 by 2, then you can go ahead and add and subtract these matrices. So A plus B simply means we are adding the two matrices, and the result is simply going to be element by element operation in the corresponding positions of the two matrices. So for example, A plus E would be performed, B plus F will be performed, so each element will be added to the other in the corresponding position. You can also do the same thing with the subtraction symbol. So A minus B, where you subtract the two matrices, you would have the very first element in the first matrix A, then minus the first element in the second matrix B. And so you would have A minus E, and the rest of them will follow in their corresponding positions. Also, when we move on to multiplication of matrices, two matrices A and B are conformable for multiplication if the number of columns in A equals the number of rows in B. Keep this one in mind because it's very important that two matrices must be conformable before multiplication can be done. So the multiplication operator for matrices in R is given by percentage asterisk percentage. If you use the arithmetic operator asterisk only, it only performs the element by element operation like we saw when we were dealing with addition and subtraction. So if you are dealing with multiplication of matrices, you would have to use these operators for the matrix operation. So let's go to R and have a go at these matrix operations. Now in R, let's create a matrix called A and then specify the data argument. Let's have some 4 numbers as a vector. So 5, 1, 6, 2, and then let's specify the number of rows to be 2 and the number of columns to be 2. And let's go ahead and extend the by row argument and set it to true so that these numbers are filled by rows. Again, let's create another matrix B and specify the data to be a vector of 4 values as well. So let's use this arbitrary set of numbers. As long as they have the same dimension, we do not have a problem. So n row equals 2 and n col equals true. The by row argument is false by default, so we leave it as such. Let me execute these two codes at the same time. Now we have our matrix A, so let's print it to the console, and we have the B, and so these are our two matrices. So the first thing that we need to check is that if you want to add these two matrices, A plus B, then you should ensure that they have the same dimension. And yes, they do have the same 2 by 2 dimension, so it is possible to add these matrices. So we add them, and that is the result that we get. So we do have 5 plus minus 3 gives us 2, then 1 plus 8 gives you 9, 6 plus 1 gives you 7, and 2 plus 9 also gives you 11. So it performs element by element operation. I would go ahead and now do A minus B, and the operation will be done in a similar fashion where we have 5 minus 3, that should give you 8, and then we have 1 minus 8, that should give you minus 7, and the likes. So that is how you perform addition and subtraction of matrices. Let's go ahead and create another matrix C. So let's have the matrix here. The data should be we want to create matrices with different dimensions, but the two matrices we are going to perform these operations on would be of the same dimension. So let's have our vector to be, say, 3, 9, 1, negative 9, 6, 8. And then let's specify the number of rows to be 3 and the number of columns to be 2. So we simply should have 3 by 2, and so there should be 6 elements there. And let's go ahead and create the matrix D. So data equals, let's have numbers like 7, 11, 0, 4, 20, 100. And the number of rows should be 3 and the number of columns should also be 2. So you'd observe that both matrices do have the same dimension. So let's execute C and D. Let's print them to the console, C matrix and the D matrix. They have the same dimensions, and it is therefore possible for you to add C plus D and you end up getting the result, and then C minus D, and you also get that result. Mind you that A and B are of 2 by 2 dimension, C and D are of 3 by 2 dimension. But let's assume you wanted to add A to C, which are of different dimensions. Then let's see what results that we get. If we add them, we actually have an error, which is non-conformable arrays. So for addition and subtraction to be possible, the two matrices must be of the same dimension. Now let's proceed to the second operation, which happens to be multiplication of matrices. And for multiplication of matrices, we did mention about what we call the conformability condition, where we expect the number of columns in the first matrix should be equal to the number of rows in the second matrix. So if you have two matrices, let's say matrix A, let's go ahead and create another matrix A, or because we have used A before, let's simply use another letter. So let's have matrix E, and then we would have matrix here, and let's create that matrix. So we have, let's say 3, 2, 4, 9. We are creating 2 by 2 matrix. So n row equals 2 and n col equals 2. Now let's also go ahead and create the matrix F. The data equals, so let's have numbers like 6, 9, 4, 0, 3, 2. So we do have 6 numbers, so we can also create 2 rows and say 3 columns. So let's run these two codes, and then let's print them to the console. So E, and then we have the matrix F. So the matrix E has the dimension 2 by 2, and that of F also has the dimension 2 by 3. There is a function in R for checking the dimension of a matrix, and that is the dim or the dim function. So all you have to do is just pass the matrix object that you have created in there. So like for example, dim E, if I execute, I get 2, 2. So the first number for the rows, the second number for the columns. I can also do the same for F, dim F. So what is the dimension of F? We have 2, 3. Now, I want you to look at the number of columns in the first matrix E. So that is 2. And the number of rows in the second matrix F, and that is also 2. Are they equal? Yes. The number of columns in E equals the number of rows in F. Therefore, the two matrices are conformable for multiplication if and only if we are multiplying E by F. Now, because the E comes first, we say E pre-multiplies the matrix F, but F post-multiplies the matrix E. Just simply, E comes first before F. That is how we actually write it. So if I should go ahead and run this code, we end up getting the multiplication. So I would expect you at this time to apply your matrices concept that you might have learned from your maths class, because there is a way that these two matrices are being multiplied, because it is not the usual multiplication symbol that we find in the arithmetic operations that we normally do. So there is a way that this multiplication is done, and that is why the conformability is required for these two matrices to be multiplied. Okay, but if you go ahead and just interchange the position, so let's say F now multiplies E, and then we should execute, we now get error, non-conformable arguments. And why is that? So let's check the dimension of F first, and let's check the dimension of E. And what happens? Look at the number of columns in F, 3, and look at the number of rows in E, 2. They are not the same. Therefore, F multiplying E, these two matrices are not conformable for multiplication if F pre-multiplies the matrix E. So we need to be very careful when we are dealing with multiplication of matrices. So let's clean this one out. Let's create another set of matrices for multiplication in order to reinforce our concept of what we are doing. So let's have data equals, let's have a 2 by 2 matrix. So -4, 9, 6, and 2. And the number of rows is 2. I can decide not to specify the number of columns. And R will figure out there are 4 elements, and we'll go ahead and create the remaining 2 columns that are needed to complete the 4 elements. And for this one also, let's have like 0, -1, 7, -8. And let's specify the number of columns to be 2. Very tricky, right? But it's very simple if you learned matrices very well from the previous video. So here, let's go ahead and create or run these 2 codes that we have written. So let's print the matrix G and the matrix H. So you observe that each matrix is of dimension 2 by 2. So if I now write dim G and dim H, I want to check their dimensions. Then we observe that each has 2 by 2 dimension, and so the number of columns in G equals the number of rows in H. Therefore, G multiplying H is possible because these 2 matrices are conformable for multiplication. And again, if I also pre-multiply the H by the G, that is also possible because they have the same dimension, and therefore the number of columns in H equals the number of rows in G. So this is how we perform arithmetic operations on matrices.